When I want to use it's just like a startup will come up on this. It's a bunch of startups. Okay, sure. Whenever. Like you will. No, we'll just go. Okay.
Okay, please, please have a seat. Please settle down. And also there are some seats in the back. And don't worry about the fact that you're in the back. You'll be able to hear us clearly. These mics are picking up our voices. It looks like I'm speaking loudly, but I'm not. And we'll be able to hear you as well. It's picking up your sound as well. Okay, so welcome to ISB. For some of you, this is probably the first time. For others, this is you've been here before. Today, we are starting a new series called Science Ventures. And the idea is that, Minister Goyal the other day complained that what's happening to entrepreneurship in India? Why are we only making ice cream and Zeptos and things like that? Now, first of all, Minister is wrong. I think all entrepreneurship is good as long as it's solving a problem. So I don't care whether it is Zepto or ice cream. But at the same time, we should do entrepreneurship, which is at the cutting edge of science and technology. That's what this series is about. And today, I'm delighted to introduce Professor Malla Reddy, who's from IIT Hyderabad. I wanted to have him as the first speaker because we wanted to set the bar really high. He sent me one of his papers, which was published in Science magazine, I think 2023. 21? 2021. And I read the paper and I said, this idea has to be made more public to see what we can do. So what I'm going to do is, we are going to have a series of conversation because the stuff is difficult. I have tried to work through it myself with him. So I'm going to ask him questions that are very simple so that we can all understand it. And if you don't understand something, also raise your hand. Clarifying questions only, not deep questions. We'll do the deep Q&A at the end. But if there's a clarifying question, like, what are you talking about? Or what does this mean? Please raise your hand, okay? So thank you. Thank you, Dr. Reddy, for being here.
It's a pleasure.
I'll say, I'll sit down. Can I sit down? Okay, all right. So you did your PhD from University of Hyderabad, yes, which is like a stone throw away.
Yes.
Okay.
Absolutely.
And what did you do? What did you study?
So, I came from a very small, village. So then I kind of, it was going to the university was a big dream. And so one of my professors suggested that's a very good university and there is a very good professor. He works on crystals. I had not much idea about crystals. So then I went and met him and I really liked the way he spoke. And then I worked on basically organic crystals. Crystals are everywhere around us, but many of us.
So tell us, what is a crystal?
Okay. Crystals have very regular arrangement of molecules or it could be ions or any constituents. For example, if you take a basket of onions and if you put basically into a box, they will arrange very randomly. So instead of that, if you take these egg cages, for example, and fill the egg cage with the onions and then stack one over the other, and then you get a very regular arrangement.
Okay.
Right? So crystals have molecules or ions very regularly arranged inside. For example, one of the examples is diamond.
Diamond. So right? Diamond is an example of crystal that we all love.
Right? So diamond is so beautiful and it shines. We all love it, right? So, but diamond is made up of carbon. The coal is also made up of exactly the same thing, carbon. You see the difference. So the structure is very important. How these carbons are arranged inside this.
So coal is not an example of a crystal, or is it?
It's not an example of a
It's
crystal.
not. Okay. So
It's
crystal, the arrangement is very tight, rigid.
Yes.
So it gives a very specific
Yes,
structure.
exactly. So I mean, like it's another type of arrangement in the core. Okay. For example, if you look at graphite, right? What we have on a pen nib, it is also purely carbon. So the structure is completely different. That's also a crystalline material, but the structure makes a lot of difference. And internal structure gives the physical properties. Like diamond is one of the hardest, stiffest materials known. But graphite pen nib, when we write, it leaves the material behind, right? Because it's very soft.
Yeah.
But it's exactly the same. The connectivity of these, atoms, the way they are arranged is very, very important for material.
Okay.
That's where, designing the crystal structures is so fascinating, because you can change the property by using exactly the same material.
So it's how the molecules are arranged that makes all the difference. So I will come to this. I think the paper is groundbreaking. But after your PhD, just tell us briefly what you did.
Okay. After my PhD, I went for postdoc in Germany.
In Germany.
So then, so if you look at in under sea, so there are some algae, even in very dim light, they can do the photosynthesis by taking very small amount of light. They can still survive, kilometers below, right? So they have something called, these pigments, okay, porphyrites. So what makes them so efficient, right? And my professor was basically studying them. And if you can crystallize those materials, make their replicas in the lab and crystallize them, and if you look at the crystal structure, that will explain why they work, because it's not the material, but the way they are arranged is very important. So the arrangement is very important. So to know the arrangement, if you make a crystal, and it is very easy to get the structure using some technique called X-ray diffractometer. You can see the molecules in front of your eye in the computer. You can kind of calculate it, and then you can see. So my job was to crystallize them.
Your job was to crystallize that algae material.
Them. They had made, but a few students tried to crystallize them for a few years. 2 students have failed to crystallize them. And they were not experts on crystallizing, but they were expert on photosynthesis and other things.
So now that you're good at it, you can make diamonds at home, right? Okay, all right. Well, we'll let that go. And then after your postdoc, what do you do?
So after my postdoc, I joined at ISR Kolkata, which is a basic science institute. And there are several ISRs. These are like, if IITs for engineering, ISRs are for basic science.
Basic sciences, yeah.
Exactly.
In fact, on the other campus in Mohali, at ISB, right next door is one of the ISRs as well.
Yes.
Yeah. Okay.
So I was there for 15 years.
In Calcutta.
Calcutta.
Okay.
So then I moved to IIT Hyderabad in 2020.
You wanted to come back home?
So
you're from here, right?
I'm from here. That's
Telangana.
Telangana. 2 hours from here.
Yeah. Okay. So IIT Hyderabad managed to catch you and bring you back.
Yeah.
And this work is with your colleagues at IIT Hyderabad?
No, this was from ISR Kolkata.
This is from ISR. So this is the paper. This is a very typical in science papers that like I write papers too, but usually I have like 2 co-authors or 3 co-authors. On your this thing, how many co-authors did you have?
I need to count.
You need to count, okay. Yeah.
It was close to 10.
Close to 10.
This is where I tell the scientists, many of my colleagues and younger ones. So see, we found this beautiful self-healing crystals. We found it. But to characterize and quantify at a nanoscale, like how well it actually healed. Okay, it looks like it.
So let's not jump ahead.
So,
I want to. Yeah, okay.
I'll tell you. So we did something, but we were not good enough to explain everything. So that is when we had to collaborate with physicists
Right.
Then
So this is a collaboration between
Collaboration.
people in the lab, theoreticians, you all come together and you sort of give ideas, they go to do some more labs, then they actually build something and come back. So it takes a while. How long did you work on this?
So it took about 2.5 years.
2.5
2.5
years.
years. And I would say for a quality of this work, it was actually really quite fast.
Quite fast.
Quite fast. I would say.
Quite fast.
Some of my work took almost like 4 years, 5 years in time.
Okay.
You know.
Okay. Very good. So let's get to it. The title of the talk is Amazing New Materials That Repair Themselves. I mean, so we know of things that repair themselves, right? So if, for example, if I take some wet clay and another wet clay and I break it and I bring it back together, it will heal itself, right? As an example.
Yeah.
And our bodies, cells do some of the self-healing itself. But this is different. Tell us why this is different.
So, so you gave an example of clay. It's a very soft material.
Very soft.
Soft material, right? So even if you take our toothpaste gel, if you cut it with a blade and put together, it will heal.
Will heal.
Even liquid, the inherent property of liquid is to, join.
Yeah, so you take a cup of tea, you pour it out, it's broken, you bring it back, it's done.
So
right.
it's for liquids, it's a natural, because the molecules or constituents can move very easily, right?
So the mechanism there is diffusion.
Diffusion. It's very easy in.
But that's not what this is.
But in crystals, where you have molecules tightly packed, they cannot move.
Cannot move. So if you break them, it's broken.
It's broken. Very hard.
So if you have a diamond, if you have a 20-carat diamond and you break it, you got 2 10-carat diamonds and the prices have dropped, right?
Absolutely.
Okay. But you're saying you have found materials that are as hard as diamonds.
Hard, I would say. Yeah.
Hard. And they have the property that if they break them, that means you got like maybe 1 millimeter apart, they kind of clap back together.
Yes.
How's that?
Yeah. So, so I think I can show you something.
Yeah, okay.
Yeah. I think this is, you can see. Yeah. So can you see this? This is a crystal which we have. Yeah. So can you mute? Okay. So this is a crystal, and then you basically push it. You hold them with the forceps, and then you push it in the middle, and then on its own there is a crack here.
Yeah, so I see that. Yeah.
Yeah. So there is a crack, and
when you let
you
it
can
go,
see here, probably, and then you just leave it. So as you can see, it's a quite big crack. So you just pull back your force, then on its own, the crystals basically pull back on their own, and then they basically come back, and then you don't see any crack line. Completely, they align it almost
they
with a molecule.
come back to the same crystalline formation as it was before.
Yeah.
So it's like your twins in Bollywood movies that got separated, right? They got back together and it's like they were never separate.
Yes, they look so perfect, even under a high resolution microscope. There's something called scanning electron microscope, and then even atomic force microscopy. If you look at even scan at nanoscale, you don't see anything. They look as perfect as what you see them, how they are before.
So it seems like that there must be some force of attraction.
Absolutely.
Tell us.
So how does that come, right? So these are not magnets. Okay, these are very simple, made up of very simple molecules, and there are no magnets here. This was a big question for us too, because there was no literature to fall back on, and we were also quite surprised, and it was kind of a big puzzle. And then I told my student that if you can solve this problem and explain why this is happening, This will be a kind of, big breakthrough, and we can publish wherever we want. And then
Yeah.
student was,
They were
it's very
motivated.
important. Somebody has to be really motivated, and he was so motivated. And then we went into the details. So this is actually a piezoelectric crystal.
So
And
piezoelectric,
Yeah.
let's break it up a little bit.
Okay.
What is piezoelectric?
so we all know this lighter, for example, right?
The
So,
lighter?
lighter, anyone
Yeah.
has? Don't use it here now. So if you basically click, then there is a quartz crystal inside. You hit it with a mechanical force. Then when you hit any mechanical piezoelectric crystal with mechanical force, it will generate electrical, potential. Okay. So if you squeeze
So this is your lighter that you use in kitchen also, right? You just use mechanical force and it generates some electricity.
spark, yeah,
Spark.
it generates an electricity. And so piezoelectric materials.
So piezo means small or
Piezo means kind of a force,
force?
driven,
Okay.
something like that. Okay.
Ah.
For example, this is your material, piezoelectric material here, and then you squeeze it. So you are kind of basically internally you are distorting the charges inside. And then once you distort the charges, so there is one kind of a positive end and negative end. So we all know that, if we have studied the +2 level science, we know that, positive and electrical charges, they attract each other. Okay. So that leads to the voltage here, as you can see on that side. So you can keep doing this and you keep basically generating the electrical potential.
So this is like the Christian myth that, God created Adam and Eve, but they were opposites. So they attracted each other. This is what's happening at the molecular level.
Yes.
So they are opposite charges. So it's not a magnet, but this is actually electric charge
At a molecular.
that brings.
Yeah. Yeah.
How do you think about this? How did this idea come to you?
Okay. So when we got these crystals, so we can understand from the crystal packing. Crystals have certain symmetry internally. And if you look at, for example, if there is a molecule and it has molecules also have got, most molecule, if it is not a highly symmetrical molecule, they have got positive end and negative end. For example, if I take all these molecules and put all the heads on one side and all the tails on the other side, so then I'm kind of making it a, polar, right? On one side, I'm pushing positive sides, on the other side, negative sides.
So this is like what you call a dipole or bipole?
It's a kind of a dipole,
Yeah.
molecule as a dipole. And then when they are arranged in a certain fashion, so basically they become, piezoelectric actually.
Okay.
So,
All
and
right.
then I go one step further and then I take this and then break it, for example, right? For example, as you can see here, if this is my crystal, right? And I have all the molecules, for example, those arrows, if you say they are molecules, on one side there is a positive end, on the other side negative end. So then this is my crystal. Inside I have molecules which are arranged in this direction. Then when I break this crystal, on one side I have positive ends, on the other side negative ends, because I'm breaking. So they are together, they form some kind of attractive forces in the crystal. Once I break them, so then they kind of separate out on the surfaces. So that leads to this attraction and then kind of snaps them back. And then since these are molecular dipoles, so they kind of arrange almost perfectly when this crystal comes back. So this is, so here.
You know that it needed some kind of a force, right? So it could be either magnetic or it could be like a spring. So if I have two things which are tightly spring and you sort of open them, it will shut it back.
Yes.
In this case, it's happening
Exactly.
with electric charges.
Electric charge. Yes.
Now, my question to you is, you actually made these crystals?
Yes. So
they don't exist in nature?
these are not natural.
These are not nature.
These
So
are
you are making them.
We are making them.
Okay,
We are making
all
them.
right.
Yes.
Now-
we are making them.
Now I'm going to jump way ahead and then we'll come back to more mechanism. What is the size we are talking about?
Okay.
Are we talking about like making a steel mill? Are we talking about like tiny stuff?
Yeah.
Where is the
So-
use case?
So here in our lab, what we made are like, few millimeters long. Okay. These are like hair-like,
Yeah.
maybe thicker hair. okay, like horse hair, you can say. So, but we can even make them even thicker, like few centimeters long also. we
Few
can make,
centimeters long.
and like few millimeters thick, like, so these stitching needle type, right? We can even make it that size. Still it works.
Okay.
Still it works. Yeah.
So now my question is this. I am a shallow person. So I say, my screen breaks a lot. If I can make it of your crystal, as soon as there's a crack, it will repair itself?
If you can make it like a thin film,
Film, it would.
yeah, it should work.
But that's not a good use case.
This is not a very
So who
useful
cares?
because yeah.
Right?
So
where is a good use case? Where do you want these materials where this kind of unbreakability or sort of repair is kind of important?
yes. So this would be kind of more futuristic.
Yeah,
So
that's what this thing is about, futuristic, yes.
so in future, we want to make everything miniaturized, right?
Okay.
So these piezoelectric crystals can also work like actuators. Like you give electrical pulse, they can expand or compress. Okay, they can give a mechanical kick, for example. So these crystals can be directly used for those kind of applications. Then when you have a micro device, right?
Micro devices.
Micro devices.
Yeah.
So then when you deploy a device in the real world, there is a lot of mechanical action always, right? If you break them, then you can't go and then repair them, at certain scale. For example, if you deploy it in for example, a satellite, for example, you can send satellite.
Satellite.
You have a micro component, for example.
Or maybe in a war situation, right? So it's very sensitive, and on the ground you can't come and bring your, right? So
Yes.
there, those materials are of critical importance,
Yes.
and especially if these are micro electronic devices,
Yes.
you want them to be in extreme conditions, like,
Yes, absolutely.
high altitudes or deserts, or that's when this will be important, not iPhone repairing itself. That's kind of a very shallow
Yes.
Gen Z application.
Yes.
Is that what you're
So,
thinking about?
yes, that's absolutely, yeah. So and other thing is that one more important thing here is that all the other known self-healing materials till now known in the literature require you to go put them together, and
You
give
need
some-
external force.
You need to put them together and then give some kind of an external stimuli, like either heating, for example, or some kind of a
Heating,
light,
glue, soldering,
Yes, you need
welding,
absolutely.
right? So some external stuff is
external
required.
stuff is required. But
This one
here-
has none of that.
Here it requires nothing. And also amazingly, if you make a crack, for example, and leave it within few microseconds,
Few microseconds.
it will heal back. So that means you don't feel that it has actually, you don't see any disruption in the function.
You may not even know that
No,
it actually.
there was actually a
So
failure.
you would think that this is really an indestructible material, because as soon as it breaks,
Yes.
okay. So then there is a difference between this and an unbreakable material. An unbreakable material is a material that doesn't break.
Yes.
Here there is some plasticity,
Yes.
and yet it's coming back.
Yes. Yeah.
Why would I prefer that versus the first one that doesn't break at all?
Yes.
What are the
Yeah.
use cases?
So if you want to build very tough materials, for example, right? So most of the time they are also not flexible. For
They're not
example,
flexible.
You
Right.
want to have a device which is very flexible, and sometimes you might go to a very extreme stress conditions, but still you might break it even if it's hard, right? Here it might break, okay? It might take all the force that you give, but it just comes back, right? And this is
So
easier
the
to-
plasticity is useful.
Yeah.
Because that flexibility is actually makes it even more durable
Or
than a very hard material, because if the hard material breaks, it breaks.
breaks forever.
It's like a heartbreak.
Yes.
Dil tod diya to tod diya, right? But we want it to be more plastic,
Yeah.
so that, something like that. So the use cases you see are in micro devices. Where else?
Micro device. So
Micro-
then there are many other, for example, electronic devices.
How about planes?
Uh,
Can we make planes safer?
so see here, the fundamental aspect of arranging the molecules, the concept what we developed. Okay, this is translatable into any material that you would like to.
Any material.
You want to have this in polymers, for example, you should be able to use these principles to build material. You can also make a very tough material. Okay, you want to have both toughness and this property both. So this is a kind of a very basic concept which will allow you to translate into many other materials and make. For example, you want to have a material panel, for example, a panel, right?
A panel.
A panel you want to make it, right? So you can take this concept. If you make a material which follows these principles, it should be able to also show the self-healing. So that's why I said it is more of a futuristic thing. We have developed a very basic framework, and then that should allow us to go into various materials. For example, to give you an example, so following this, we wanted to see if you make a semiconducting material. This is not a semiconducting.
This is not a semiconductor.
Right. We know that semiconductors are very, very useful in many applications. So we made in our lab a semiconducting material, and so that material has very, very interesting properties along with the self-healing property. Okay. For example, if you want to use AI uses a lot of cloud computing. Right.
Mhm.
For example, if you have our material, so this material is such that you can. It's called analog material. It's like more like a neural network kind of a material. So you can basically, instead of 0 or 1 like binary, the crystal has such a special property that you can have 1, 2, 3 up to 2 to the power of 10 states.
Which is about 1,000. 2 to the 10 is
Yeah.
about 1,000. Yeah.
Yeah. 10, 1024
Yeah.
states. You can have a lot of states. So this allows you to use it for analog computing, which more works like neural network. Okay. It's a beautiful material. In that, we have brought the self-healing.
I see.
Okay.
I see. That's actually very insightful, right? You're
Yes.
saying most of it's 0, 1,
Yes.
which is binary,
Binary.
but this can have many states.
Many states.
And the reason the 0, 1 thing was very useful was because 0, 1 is easy to make.
Easy to make.
But
Easy to make.
having materials that have many states is very hard.
Very hard.
So you can simulate analog type of stuff with this thing.
Absolutely.
I think that's really brilliant. Yeah.
What is the use case of such materials, right? Analog material will allow you to basically compute locally. For example,
Right.
I can ask you, for example, you take your mobile, okay? Then you go to your Gmail, switch on your Wi-Fi, okay? You keep your data on, and then you, for example, you want to email to your friend, for example, and then as soon as you enter the email ID, and then you go and you write dear, then automatically it will take the name, right? Okay. Then you delete that draft, and then you switch off your mobile data, and then you do the same thing again with another name, for example. Then you type dear, it won't come. It won't alert you because the AI actually used, and you are using the cloud computing, okay, through the internet. So you are basically exporting the data. So to compute, use the AI and the mobile, you need cloud computing. For that, you need internet. So you are transporting the data. That costs a lot of energy.
Yes.
So the materials that we built with this, neural network type of memory.
The computation
so
can be local.
If you have it on your mobile, you don't need internet. It will do these. AI will use actually local. When you are storing your data, it can, store your data as well as it can be used for computing as well locally. Okay,
I don't know if it's happening to you guys, but my brain is like on fire. Do you guys see the applications here? Because the trouble with cloud computing is that anything that's on the server in the cloud is going to be hacked, right? So one way to avoid the hacks is to have only local computation. But the local computation, there isn't enough.
That's where you need.
That's where this can help.
No, self-healing is actually inducted into the material with those properties. Okay, we have got the beautiful, these neural network type of property as well as the self-healing. Both we have incorporated in a material, and one of my guy who is sitting here is working on the project. here in the front.
Who is that?
Here,
Can you please stand up?
Get up.
Yeah, okay.
And
So
so-
you're saying the application is not on the screen, it's actually on the inside.
inside.
Ah,
So you
that's
can
brilliant.
use it for local computing. Okay. For AI, you are going to burn a lot of, you are going to use a lot of energy if you are going to use AI everywhere, right? You need computing which is locally done as well. So this can, if you have self-healing property in a material like that, it's a very cheap material. It's lightweight. You can make it in, even
Okay,
in-
you use the magic word. I'm an economist. Very cheap material. Tell us more about that. What do you mean by that?
he can make a few kgs in a couple of days.
Few
Okay.
kgs?
Yes, it's very cheap. It's very cheap.
For how much?
So for entrepreneurs, for my investors, this is like music. Because I was just about to ask you that all this is, but if it's going to take, crores of rupees, then it's not worth it. But you're saying this is actually, and it can be scaled?
It can be scaled. It can be scaled. He's working on that. By the time,
So he can do
by the time he
is in a day. If I were to know. No, I'm asking because there are people here who are listening. Some of you are listening from elsewhere. If I wanted to create like a ton of this material on a mass scale, can this be manufactured?
there are my friends sitting in the audience who are working on bulk drug manufacturing. You give it to any pharma company, you want 1 quintal, they can do it. Some of my friends are here.
That's brilliant. That's brilliant. So, Piyush Goyal ji, I hope you're listening. What I like to do is go to the audience because I'm sure their brains are on fire as well, and they have questions. But is there something we didn't cover that they should know? I mean, there's lots of stuff they should know,
Yes.
but is there some critical things, 2 or 3 things that I didn't get a chance to ask you about?
Okay, yeah. So what I would suggest is that generally in academic institutes, we do things very, very deep, okay? And we are very passionate about it. And then, many of these can be scaled up, but we go only up to certain level. And then unless there is an interest from somebody, we would not take up that to, make it
Yeah.
like a finished product. So that's how normally it works. And then we have many other interesting problems, right? We are more excited about that. So this is where there should be more interaction so that, people,
So it's a relay race, right? These guys are willing to run the first 100 meters, but if you need to go to the whole mile, they need to pass the baton on to the next one who says, okay, I'm going to scale it. I'm going to fund it. Defense will say, I can find an application for it, and then it will proceed, right? So we need to have all those markers where you can pass the baton on. Is that right?
Absolutely.
Okay.
So normally this is a very deep science, based work, right? Some of these require, some amount of time particularly, and also people to work on it. So, and then we also need to understand the perspective of use case also, right? So this requires a lot of interaction. So that is where I think we currently miss this interaction part in a big way, actually.
Are you open to it? Because academics sometimes are, hard-nosed about. They don't want to do anything to do with applications.
So like that was the case. You're absolutely right. Maybe when you are a PhD student, right? But now I can guarantee you, young faculty in academic institutes are very, very, enthusiastic to partner it. And this is kind of, also something that everybody would like to do nowadays.
Okay.
So you will
So
not.
if I have an investor who says, I want to fund it, I want to do this, connect me to Professor Malla Reddy. Would you talk to him or her?
Absolutely.
You would.
Absolutely.
Okay. No,
And
it's
so-
very important because some academics said, don't bring me the real world, I'm ready to write my next science paper. Okay.
So you're right.
Okay.
So we patented this in India as well as US. Many of these molecules are patented.
Has there been similar work done elsewhere? Are there other materials like this?
So not by using this mechanism.
Not this
This
mechanism.
mechanism where they come automatically on their own and snap and then heal at almost with atomic precision. So this was not done before by anybody. But there are few people in the world who are working on crystals. You can count people who are working on crystals basically like on your fingers.
On your fingers.
Just few people. all of them I know very well. Like, just some of us who are working on crystals have actually kind of found this.
I think it's truly exciting. I want 10% of everything you get, okay? Let me actually, can I go to the audience and see if you have sort of questions about the science, this thing, please, yes, sir.
This, whatever you have seen, these materials are mostly organic material, correct?
Yes.
Because in semiconductor, mostly they are using rare earth metals, which is very costly. So you mean to say that since this is a simple organic material, it is very cheap?
Yes, absolutely. So, see, there are material, normally right now, most people have used only inorganic rare earth materials for various applications. This may not basically replace them everywhere, but there are alternate methods to do the same thing using cheap materials like this. So here again, a lot of electrical engineering, a lot of design, all this would come into picture, particularly the medical devices, right? So in those cases, wearable devices, all these small IoT things, right? It's not very expensive, but as long as it functions properly, you are fine. After a few years, you can replace it and then make another one. So, but as long as you have it, it should work robust. So this is where, since organic crystals are much more softer compared to inorganic materials, and properties like this are very much essential. You buy it, you throw it, then immediately if it breaks next day, right, nobody would buy it. But if it, if you incorporate these properties, robustness and all, then it becomes viable. This is where the community is now trying to, strengthen this field. Thank you.
Let me take a few more questions. Let me go way in the back, the gentleman in the white shirt.
Yes.
Have you compared the mechanical? What's chemical name and post healing?
Yes, we have done it. So see, here, more than mechanical properties, semiconducting property is very important. So I was giving a talk at IIT Hyderabad. One of my colleague, very young assistant professor from electrical engineering department, stood up and said that I don't believe that this is a full self-healing unless you show me that after breaking, the electrical conductivity is exactly same. So after joining IIT Hyderabad, then I put a giant student. So now he has done all the measurements. So now we see that the conductivity is absolutely same. You don't see any difference. So that is a part. So mechanically, we have also done that, but mechanical strength is not 100%, but it is little lower.
I come from a background of yes. So you said that this can be expanded in whatever.
Yes.
I was thinking from that perspective.
Right.
Has this being done on temperatures or pressures?
Healing. So we have done it low temperatures, so it works very well.
Temperatures.
High temperature, so crystal is stable around up to 200 degrees centigrade. So it works up to 200 degrees centigrade. So, but it is always possible to go up to 300 degrees centigrade with organic crystals. But beyond that, most of the organic crystals won't survive.
Yeah, so don't put it in a furnace. Room temperature everywhere will be okay.
Airplane application, right? I was thinking about windshield for airplanes.
Windshield for airplanes.
The temperature.
But what is the most critical part of the plane when it fails? We are in trouble. That's what we have to think about, right? Is it the windshield, the most critical part, or something else? I mean, I don't know the answer, but I think in general, that's what we need to think about. What is the material where, criticality is really important?
Yeah.
Can I use that material there? And then we know we got. So in my example, this is not the most critical.
Yeah.
So something like that. Yeah. Bunch of other questions. Yes, sir.
Can it be done for graphene as well, these materials?
No,
property?
see, here the material itself has to be designed in such a way that it has an inherent property, like self-healing property.
Yeah.
You cannot use this material to heal something, which is a totally different material. Okay. So it's not like something like a Fevikwik or something else. Okay. If I can draw that analogy. So it is the property that requires to be designed into the material. Okay. So
Graphene is also very strong material. It's 1 nanoatom thick and it's getting high potential and high demand globally. and which is in buildings.
But by the way, somebody showed that if you make a diamond like a nano rod,
Yes.
even that cell heals.
If that cell heals.
Even that cell heals. So at atomic level, but that only works when you do it in a inert environment like vacuum. Okay, because once you break the carbon bonds, right? If you have oxygen and around, so then these radicals basically react and then it can't heal. So under very confined condition, if you break the covalent bond, still it can work, but it works very well in the molecular materials.
But I've seen some application in batteries. The fastest charging batteries coming from China, and they're incorporating a lot of these features into that. And within 5 minutes, they can charge some 800 kilometers. And now there is a new.
So what's the relevance here with the high charging batteries? What's your idea?
Material, some properties can be used to that.
So for example, electrolyte, if you can use a self-healing electrolyte, for example, these micro cracks, crack is a very critical thing. For crack.
Yeah.
If you have a crack, then that will build up the charge, right? It can break down the battery. So if you have your components, all of them are self-healing, so then you can save it from the mechanical cracks. It can work that way as well.
Yes, sir. Yeah.
Basically, I'm a commerce student, but I have heard many a time the explanation being made crystal clear. That word I have heard many times. Now I understood the concept of crystal is basically the arrangement of the molecules. That explanation is crystal clear. So I have correlated with it.
Yeah. Okay.
Yes.
I heard many times the explanation is crystal clear, but now the interaction and explanation made more clear. And my question is, can this crystal be applied in making construction material?
Okay, very, very good question, actually. Yeah, so not this material, but you can use the concept and then make materials follow this crystal structure. Okay, so for other electronic materials that I was talking about, so we use the concept. Then we made a new material which has both electrical conductivity, interesting properties, as well as the self-healing properties. So one has to design, even in the polymers, I was saying that you can use the concept. So what is the concept here? You have to align all the dipoles with all heads on one side, all tails on the other side. So even the biology, which you said, right? So tissue has all chiral molecules. In that also, all the dipoles are arranged in that way. In a way, we are proving how the self-healing works in biology. So
in your paper, you mentioned that you took inspiration from nature somewhere, right?
Yeah, no, we said that self-healing is something that people have taken as an inspiration from nature and then try to work out. But mechanism itself is not,
This is
made
very
clear.
different.
And
Yeah.
from our example, this is becoming very clear. Now we are working on more biological materials, and then we are going
But even in biology, I think your analogy is right. You still have a DNA. So there's somebody actually has giving instructions, right? This one has no instructions at all. It's purely the property of the material that it creates this attractive force,
Right.
which just slaps it back together, right?
Yes, yeah. So even in the biology, it is the way the molecules are arranged basically lead to the self-healing. So it's not directly the DNA, but DNA instructs on how to make the molecules. And
Right.
here I am actually doing that job. You
That's
can say
right.
that I am directing my material, but in the nature, DNA directs the materials to self-assemble in that way.
I call that external too, in a way. Yeah.
What I
Yes,
could
sir.
infer, just an extension of that. What I could infer is there is a widespread application of this material, but where is the more value add?
So I don't think construction is the most valuable, right? See, in construction, you can correct me, because there, if you want to make something harder, just use more of it, right? Or, in many things, redundancy solves the problem. You do more of it, or, but where the criticality is important, if something breaks, the whole thing will break down. That's where I think this use might be.
You are right. High value, what you said is a high value,
Yeah.
Use case. But there are people working on even self-healing, construction materials as well. So, but that is not for making a simple house. But if you have to have something very specialty, material.
Some parts, for example, right? Critical
people have
parts.
been using certain materials.
Fix Bangalore roads, maybe.
Yeah. So, but here, other important thing I should make is that a small crack in a material is a starting point for any failure.
Right.
Okay,
Right,
maybe
right. So
for
this
a
is it,
large
yeah.
material, maybe initially it is very small. Unless you sort that out, you will not be able to sustain for long. So then it will propagate over a period of time with more mechanical loading cycles, and eventually there will be a failure.
It is said to be cast.
Yeah, let me, can I give chance to this person? Next person, thank you.
Have you
Yeah.
studied the voltage characteristics? Because when you're talking about analog, right? Like
Yes.
generally you want it to be 140 nanometer and like longer, but digital actually wins out because you can go down to 1 to 2 nanometer and you can just do more of that. So is it different or is it similar as silicon oxide? Like
Even length scale.
so if you want to make analog semiconductors, right? I mean,
Right.
essentially end of the day, both are the same semiconductors. One you use in the range, one you use like only 2 states. But digital is winning right now because you can just manufacture it at scale and get down to 1, 2 nanometers. While in analog, you want to stay at 140 because the voltage characteristic, you want it to be like spread out, right? To be able to control it.
Right.
So is the characteristics of your material in semiconductors, is it different than what we have with
No, see, so here we have done all the basic stuff on a single crystal, which is of the size of few millimeters long. And the devices that we have made, the channel length is around 50 microns to 250 microns. Okay, at that scale, we have shown it. But if you make thin films using the same material, we can go down to nanoscale as well. So that's the next step that we are working.
Okay.
Yeah.
The gentleman over here, then Nasira, and then I'll come to Karan.
Sir, what about the optical transmission of these tubes? Can it be used as a replacement for the fiber optic cable?
Absolutely, absolutely. Yeah, you can do that. And then we have also seen that light transmits without any deviation when you basically self-feed. It works very well. Yeah.
Nasira?
Sir, I'm doing a venture in health, and so most of my questions will be related to that. So when it comes to health tech, a lot of the devices is the problem with it is accessibility because of the cost involved. Now you're saying that your material is low cost. So have you been approached or are you in collaboration with somebody who can help with this in health tech devices, some things like stents or pacemakers, where it will be, where, if it breaks, it does not lead to major causality?
So you are right, but this is where, a lot of interaction is required. I really do not understand what exactly is required for a medical device application. The more interaction will give me, the insights on how this could be applied. But definitely this will have, I'm sure.
When you talk about cost, and
Yeah.
we're talking about accessibility, because it's not like that healthcare should only be limited to people who have money. It should go triple
Of course, of course.
down to the bottom.
Right.
So a cost of devices is a major concern. So like your material cost, it will definitely help on this.
If it is replacing something, right, any component, then we can definitely see a cost cut. If it does still the same thing, right? But we need to know what is that use case. What are we replacing it with?
Makers.
Which component? It has many components. So if there are electronic components which can be replaced with this, if the function is met by it, definitely it will help.
So
we need to
let
see
me,
those components.
let me come to Brigadier Navneet Dagar, who's, I'm going to invite you. Can you come and join us here? He has a question, but I also want to introduce him because we were talking earlier about creating this corridor of talk between defense and science and entrepreneurs. So please welcome Brigadier Navneet Dagar. You can start with your question and then we'll talk about.
Question is that now human body is one of the best examples of healing. So it takes time. And in combat situations, where there is a gunshot wound or in accidents, and this material heals in microseconds.
Yes.
I think that's a great application. You think there's a possibility there?
Yeah, but if you make any component with this material and if that breaks, then it will heal very fast. Okay, but for wounds, we cannot put this material and it cannot help in that particular aspect. Yeah. So, but if you are making any any material or any component of any device or something with the material which has self-healing property, definitely this will be a very big advantage because it heals very fast.
So let me take this chance to introduce Brigadier more fully. Tell us about you. Tell us about you. You started with NDA almost 30 years ago, and then you are a third generation. You were telling me?
I mean, if you include my training, I've been in the Army for almost 34 plus years. And I must say that in 34 years, I've never been ambushed. Today I got. I was told that I'll be coming to a place where there'll be some defense, tactics, strategy. Talk, and I have to listen, and I'm just going to be, maybe giving some suggestions and valuable inputs, but I never knew this was the level and this was the audience. So I'm pretty rustic at the edges when it comes to science, technology of this nature. But yes, I've spent, since I've spent 30 years serving the nation.
Where were you all these 30 years?
I have served all over the country. I've served in the desert sector. I've served in high altitude areas. I've served in counterinsurgency operations. I have represented the country, that is the army, as a UN military observer in Sudan. I have been an instructor in IMA, which is our pre-commissioning institute. I have commanded a tank regiment in high altitude area in Eastern Ladakh. I commanded an armored brigade, which is a combination of a number of tank regiments, somewhere in the desert sector. I have done counterinsurgency operations in where whatever has happened, sadly, a few days back, and also in the Northeast. I have, since I am from the mechanized forces, so I have a fair bit of, technology in my veins. And I can relate to piezoelectric crystals because we use it in our weapons even today. And now,
Okay, tell us where in the, whatever you're allowed to tell. Now he also knows a lot of information that he's not allowed to tell. He told me if I told you, I'll have to kill you. So I don't. Yeah.
it comes with the, great power comes with responsibility kind of a thing. So I mean, if I have a pen, I can tell you where it is used in 10 seconds. Something on the board. I can scribble.
Okay.
Marker there.
Right there. Here.
Yes.
Yeah. This is our eyes are always on the marker.
Okay. So, you are aware of how you have to defeat a tank. So what do you do to defeat a tank? So tank is an armored vehicle. To defeat a tank, what do you need? You need kinetic energy. What it implies is you need a round which has got high kinetic energy, which can strike at the enemy's tank and destroy it by penetrating it and causing disruption inside and possibly causing the ammunition to light up or anything. So for that, what do you need? You need a big gun and a lot of firepower behind that round, and you have to propel that rod. That rod has to be made of a very strong material which can penetrate the enemy tank. So you can't do that all the time, because firstly, to provide so much energy, you need a lot of firepower at the home end. So there is something known as an explosively formed projectile. EFP means you have a material over here, which is copper, and then you have explosive over here, and then you have a small standoff rod, and over here is that piezoelectric crystal.
Okay.
What it does is, when this thing strikes the enemy tank, this piezoelectric crystal gets pressed first, and in those nanoseconds, it sends a signal to there's a detonator over here. It's connected electrically. There's a wire which connects this. What happens is this piezoelectric crystal is sending now a current to the base detonator, and this lights up this explosive. This explosive creates enough heat that melts this copper. And this becomes an EFP, explosively formed projectile, means it becomes a jet, a molten jet which is at very high temperatures. And this jet then literally melts the armor and gets inside and causes disruption and destruction. This is where we are already using it. Now, this is an expensive piece of crystal. But you said that you can now make it cheaper.
Yes.
And your the temperature variations at which it can withstand are also quite high. So this is a use case. I can give it to you right now.
There you go. Ladies and gentlemen. But tell us a little bit more about what Dr. Reddy is saying. How can we make these conversations more regular? So that the ideas can flow from you folks, telling them what you need, and vice versa, they can give you solutions. Can we create some mechanism? We don't have to answer this question right now, but can we think about it? What would be a way to think about it?
I think the most important thing is visibility. I mean, this is the first interaction of the kind that I'm having. I never knew that, there is research at, such level happening. Or there is a lot of research happening not only in the IITs, various other research institutes, even in the defense industry, the civil industry. And I can assure you, anything and everything which is being done out there in the civil industry or the civil defense industry or with the IITs will have use cases in the defense industry. And when you look at defense as such, do not only think army, guns, tanks. Under normal times, we are training, maintaining, and sustaining ourselves for that ultimate task, that is the defense of the nation. But besides that also, we are doing a lot of things. We are supporting the entire economy of this country by providing employment, by providing a place where you can come and sell your goods, your weapon systems, anything and everything. Under normal circumstances, what is the worst case scenario for any country? War. You're absolutely right, war. So what is it that you can do to prevent war? Deterrence. How do you create deterrence? By creating a technologically superior army. And this is where I would suggest that if our interactions increase, then I will know, okay, such a thing exists. If I interact with the academia, and the academia often reaches out to the army, and army is not an isolated, an organization which is working in a sphere or a bubble of its own. There are touch points. I'm a touch point. Like today, somehow somebody reached out to me, and here I am interacting with you. So if we have this,
that's brilliant
network, as you said. So where we can have me interacting and learning what you can make for me, and you guys coming and interacting with us and understanding that what are the nuances we are dealing with daily. You'll find that there is so much that can be done. And the examples are right there in front of your eyes. And when you think army, again, like I said, don't think tanks and guns. There is transport management, there is medical management, there is our routine financial management. Somebody is managing my pay and accounts. Somebody is managing our supplies which are coming to, somebody is feeding the army. Somebody is providing fuel, somebody is sending rations. We are all doing it. Of course, a lot has been automated, but a lot of things are archaic. That is where you can contribute. So look at army, defense, security forces as a whole. And not only think war, borders, defense, attack. Think anything and everything that you do daily, we do it, and we do it in a much more disciplined fashion.
So, Brigadier, it's true. If you look at, for example, many of the technological advances that happen in the US, they all started in defense, including the internet. So there is a good example of, and we know Israel does a lot of cooperation between entrepreneurs and their defense thing. So I think we need to do more of it. So now what I'm going to do is I'm going to open it up again to you. You can ask questions to both Brigadier Dagar or Professor Reddy. Or me, but I won't be able to answer those questions. Yes.
For you. So you said that this can be used in semiconductor applications. So have you tried doping and creating PNP junction And like similarly in mechanical, have you tried resins and yeah, composite materials?
So our specialization is making the semiconducting materials using the molecular materials. Okay, that makes it very cheap, for example, and you can scale it up. That's where I come from. So in molecular materials, the amount of research is very minimal compared to the inorganic and other material. So this is where there's some area called advanced materials, and in that right now the molecular materials is a very small subset. But there is a lot of research that is happening in other countries, but I think we are yet to pick up, and so this will only go up. Definitely, this will have. I'm sure.
Would you talk about?
No, there's some,
Echo.
go ahead, go ahead.
We have not done so many of those yet, actually, but this is where we are trying.
But for semiconductors,
I
we
know.
need it like doping for the
Yes.
Transistors.
It's chemically inert, small chemical.
What level, right? So
Usually in pharma, there's a called as glass line reactors. So where chemical reactions takes place inside a glass lining. So the reaction, it should not interact with the vessel or take anything from there. So if we can use this instead of a glass lining to carry out the reactions, because glass lining has a very less lifespan. It's like 1 to 3 years. We have to keep replacing those machines.
okay, so it's not a very tough material. Okay, so I don't think it will withstand in solvent conditions particularly, because it can easily dissolve. So, but if you make a polymer material like a kind of a Teflon, which does not dissolve but has this property, it can help. So the fundamental message, kind of universal. You can take it to any material, but you should figure out chemically how you make that material, but still have this kind of a structural arrangement. If we can do that, then definitely we can design more and more molecules. Yeah, but with this particular molecule, it's not possible. It's matter of time.
Yes, ma'am.
So, interesting work. My question is like, do you also see any, like the application of these molecules as in biomedical applications like 3D printing, where it'll be like, we need some materials, which is like, as you said, like it is self-healing and it'll be very much required in this area. That's what I wanted to know. Have you explored it?
No, 3D printing, we have not explored for it, but we have to see the details of it actually, like what exactly is required. But in biomedical applications, definitely these materials could be components in many micro devices or, in electronics and many areas. So, and if you want to create very small electrical pulses or, even sensors, right? And you want a very high precision sensor, right? Molecular materials could be very good because they are very soft. So even a small touch can create this anisotropy, right? I mean, there could be many applications, but at the same time, since these are soft, they are very much prone to the fractures. If we can create, self-healing materials, so that can basically make it viable. Yeah, thank you.
Okay.
How hard is this?
So we check the elastic modulus is about a 13 GPa and hardness is about a 0.3 GPa. Maybe 0.3 GPa is like 10 times softer than the glass, maybe 10 to 15 times softer than the glass. Yeah. Yes.
Does it float on water?
Huh?
Float on water.
Okay. We have never tried to water it.
So the
But,
density,
the
density is asking about the density.
I know. Maybe yes, but I have to see. Maybe yes, because this is a crystalline material. So I have to see. Density of water is around 1. Right?
1.
So this is normally the crystals have about the same density, little higher than the water normally, because these are densely packed, right? But this will be very close. I'm not 100% sure. But we can easily make a lot of self-healing. We have now many examples. At least some of them will float. Yeah.
Can this material be applied in laying roads? Because budget allocation, government budget allocation is much on the roads, roads and infrastructure. Can this material be applied in laying roads?
Is that the most critical use though? I mean, you have to think about that. I think the devices where conduction is very important. I think that's where the criticality is. So if there is some kind of a guiding stuff on the roads, I think that's where I would think there might be some use.
Yes.
Or guiding of vehicles and stuff like that, where it's critical, it would be used. But
Because of rain conditions and all those things, roads well laid off also getting.
Yes, but see, when you talk about this very big infrastructure, so you need a lot of other parameters as well, right? It has to be hard enough, right? I mean, you need to meet a lot of parameters.
Yes.
So this material itself may not be useful, but there could be other materials which, if they are cheap enough, the concrete is so cheap, we cannot beat it with anything else, right? If you have to synthesize
From
some
the cost perspective,
it would be very tough.
so what you have done, Dr. Reddy, is that you have suddenly made material science sexy. When I was studying material science in IIT, it was a boring topic for me. I was not interested. But somehow now material science is back in action, and everything is about material.
It's actually, even in the scientific community, if you see the subset of papers coming from material science, it's a big component.
Yeah,
This is now really the hot.
this is the hot thing. Yeah.
Scientifically also in the community, it's one of the hottest.
This works, like you said, so optical fibers also, so it is transmitting light as well as you said electric currents, signals.
Yes.
So, I mean, another use case could of course be, like we have our communication centers out in the field.
Yeah.
They get disrupted by, let's say, kinetic action,
Hmm.
by splinters or anything. And communication is the most important thing in any setup.
Yes,
especially military.
absolutely.
And so all these wires which get severed can self-heal, and then the communication can be restablished.
Yes. Yeah, it could be useful, but I think, but then again, if you have to make a crystal which is very long, at that scale might be difficult, but you could always make composites, right?
Which are those critical junctions where
Yeah.
communication
Yes.
can fail,
Yeah,
those breakages, those can be made by.
those could be.
So colleges have these commercialization departments, right, where they want to get your, like, whatever you researched to startups. But like, can defense also have like a unit where they can be entrepreneurs in the center, where some people can go to you and be like, hey, what are your demands? Because the tender process is really like hard to get into.
So if you are aware, there is a DAP 2020, which lays down the procedure, and you're right, there is a tendering process which is long. But also now, to encourage civil defense industry partnership, we have started something known as under the ADB, Army Design Bureau. In fact, there is a complete list. It's available on the internet. There is a list of problem statements which are available. Clearly, there are a number of problem statements listed out. And in fact, this could be one of them. So you can go see which are the problem statements, and you can see in your startup world which are the things which you can make good in a quick time. The address is given there, the contact person's number is there. And let's say you have an innovative idea. Again, that contact is given right there. And in that case, up to a particular amount, and if your case is viable and is doable within a certain period of time, you can get funded. You can contact that person, given you the name, Army Design Bureau. Just log on to the internet, Army Design Bureau. You can just contact that person, present your case, you'll get an audience, and you'll get the funding. And if it is worth it, then it'll be taken on in through the fast track process. You don't have to go through the longer trending process.
Okay, that's useful. Yeah.
This is actually a two-part question. Number one, you said it is sensitive, right? Electrically sensitive, the material. What is the smallest scale? Like, I mean, for example, can it diagnose tectonic activity for, so earthquake prediction and stuff like that?
Okay, you mean the mechanical?
Yeah, the mechanical part of it, and then relay that message. Would it be possible? Sensitivity basically is what.
Oh yeah, so these are quite sensitive, but you mean piezoelectric effect, right? Yeah, so these are quite sensitive, but I'm not sure, like, what is required for it to be little in advance compared to the actual earthquake, right? So, yeah.
Fair enough. Second question would be then, if these can produce electricity when there is kinetic movement, can they be moved into fabric to generate electricity or something?
But do you
We
want
were
to?
talking about tiny amount of like,
Massive flags though.
no, no, no.
Yeah. So if you have piezoelectric materials, it's possible actually, but whether that will be economically viable if you make it at that scale is what has to be seen. But scientific community is certainly trying to, harvest energy from the sea waves and things like that by laying down piezoelectric materials. But right now the cost is still not, at a level where you can create it at a mass level. But organic materials could be very good. You need a very high piezoelectric coefficient, right? From a gram of material, how much electricity you can generate. So that will determine the cost, right? So we need to have a very high piezoelectric coefficient. And if it is also sensitive enough to give you electricity for a very small mechanical motion, so it will be very good. People are now trying to find out. Earlier, all the inorganic materials were used for all applications. They were very expensive. But now with the molecular materials, this is certainly possible. Yeah, thank you so much.
Okay, so I am going to thank both Dr. Reddy and Brigadier. What we'll do is we'll break. We have some refreshments outside, but please use that chance also to meet each other and talk informally. And I'm thrilled with how this session went, and I'm looking forward to more such sessions to bring to you and create a little bit more interaction amongst many different people, especially scientists, entrepreneurs, investors, and defense. So thank you all very much for listening and being part of this. We would like to give a small memento to both of you so that you will remember us. Let me start with Professor Reddy. We want to make sure that your slide is in the back, so please, yes. Thank you so much. And please come. We want to make sure that your slide is here. Yeah. So thank you very much for coming here. And thank you all very much. And those of you who logged in from YouTube Live, thank you. And we'll do this again soon. Okay? Thank you. Thank you all.
Thanks, me.